know if you can see it, but there is, it looks like hair going in the other phase. And that's not, that's because it's not equilibrated. So this meniscus is located at 5.8 milliliters. This you can see it if I turn it right. There. You see the meniscus at 5.8 and the 9.6 milliliters total volume. Okay, it looks to be 9.7 on the screen because it's not vertical. So what I do, I shake the mixture with the pipette, which probably use as much solvents that my finger would do. But you know, the problem is a little part of the mixture stay in the pipette and make mistake in the volume. But that's what, for what we are doing, it will do. It's okay. So now you're sure you have two phases, because I shake it as I can pick up the upper phase and put it in the lower phase to be sure it's well shaked, and pick up the lower phase and put it in the upper phase. So I'm sure it's approximately well mixed. Problem is I have small amount staying in the pipette. Okay, I can check. If I have 9.55 instead of 9.6, I know where the mistake is coming from. I do have 9.5. Okay. Yeah, that's okay. Now, what I do, I read this meniscus position, which is thick. I'll wait a little bit to be sure it's separate well. And now the new position of the meniscus is at 5.1. So I write down, I have 9.6 milliliters, lower phase 5.1 milliliters, upper phase 4.5 milliliters. Okay, whereas you can see the numbering there. Okay, so lower phase up to here, 5.1 milliliters, and upper phase 4.5 milliliters. Okay, so it means the point I prepare, 50%, 30%, 20%, is located in the tie line at a position which correspond, I should make a new drawing. By hand, we have no time, okay? Okay, I prepare a composition, say 50% water, 30% THF, 20% hexane. I can see the amount of upper phase and amount of lower phase. And I know the amount of upper phase time, suppose the tie line is like this. Suppose, I don't know, we'll see. I know that's the amount of upper phase times this distance is equal to the amount of lower phase times this distance. So in that case, I would have a big difference between upper phase and lower phase because the point is very much not in the middle. Now, with what we got, I got this lower phase 5.1 mils, upper phase 4.5 mils. So it's close. So my point is close to the middle of the tie line. So I can calculate it has no meaning with the little drawing I did by hand. Close to the middle would say it's approximately an horizontal tie line. But when you do it carefully with millimetric papers, you can really find the positions that will exactly fit 5.1 millimeters times this distance from the point on the binodal curve to the point you prepare equal 4.5, which is a little bit smaller, so the distance is a little bit bigger, time this distance to the other side of the tie line. You can find only one line that will have this relationship obeyed. All other line, it's too short on the one side and too long on the other. Only one line has approximately exactly the right value. 51 time distance on the left, 4.5 time distance on the right. Okay, so this is to give you indication. The best is to take the upper phase in the gas chromatogram, inject, and get the peak area of THF. We have hexane is very easy to determine by gas chromatography and THF also. Get the peak area of the two. Same with the lower phase, get the peak area of the two, and then you have the composition. And if you need water, the technique is called Carl Fischer. You can take a little amount, a known amount of upper phase, and get the Carl Fischer titration, giving you the water proportion. And same for the bottom phase, and you have the exact amount of the phase that you can put on your phase diagram. And it is required that the composition you get there, the composition you get there, and the 50, 20, 30 we prepare, all three are aligned. That's the tie line definition. And usually, if there is no error in the measurement, it works pretty well. That's it for what I wanted to say on the phase diagram. I know there is a lot of calculation, but it's not very difficult once you make one or two. It's really doable by student in one day. Questions? The temperature is really important. That's true. This is isotherm phase diagram. When it's a phase diagram published in a physical chemistry journal, it says temperature 20 degrees, temperature 25 degrees. You do have differences. The binodal line change if it's warmer or if it's cooler. On my own observation in CCC, it doesn't change significantly on the drawing. Why? You see this dot we did on the first experiment. We found 0.8%, if I remember. That's the next page. 0.8%, we found 0.8% hexane. When you draw the line with your pencil, the line itself is approximately 0.5% wide. So you would make at 25 degrees, it would be difficult to see the difference. Of course, I am an analytical chemist. A PChem chemist would say, wow, it should be very carefully regulated in temperature. But if you work that way, you cannot do anything. So, since you have this question, I will tell you that what we did here, it's mass phase diagram. We use mass, okay? Because it's convenient to show and click, it becomes to 0. That's very easy. You can go volume phase diagram. A PChem chemist will tell you, no, when you mix hexane and heptane, 1 mils plus 1 mils, it's not 2 mils. How much is it? It's 200.15. Okay. For me, analytical chemist, it's 2 mils. If this phase diagram we did in mass I want to have it in volume, because when you work, you prefer volume, measure volume. You will calculate all masses I wrote there, convert in volume. I can do one if you want for water, it will be easy for me. You want to convert 1.493 grams of water in milliliters. Since the density of water is 1, that's 1.493 milliliters. Okay? Then the second one is 1.49 gram. Yeah, it was the 50-50 line. So that's the same mass in THF. This is not 1.49 gram, 1.49 milliliters. THF is 1.88. I need, again, my calculator on my Excel computer software, if you prefer. And 1.49 gram of THF make exactly 1.68 milliliters. 1.68 milliliters. And same with hexane. 0.025 gram make a little bit more in milliliters. Then you add the volumes. Instead to make the total mass, you make the total volume, and you have the percentage in volume. And you can work and draw the same diagram that will be a volume diagram. It's not very different from the mass diagram. It's a little bit different. Then, drawing it, you can see the difference. If you go mole, because you can go mole, I can say 1.493 gram of water. You know that molar mass of water is 18. It's 1.493 divided by 18. This is 83 millimole of water. And that's a certain amount of millimole of THF and millimole of hexane. I can sum the millimoles and work in percentage, molar percentage. And this is very different as phase diagram, because 18 is very small and give a lot of molecules in a small amount of water, much less molecule in the same amount of THF. So in percentage, you see the water space expanding dramatically. So for your question about temperature, yes, temperature is very, very important. But as long as you have water in the system, in CCC, which is 90%, maybe 99%, I don't know, of the phase diagram we use, it's not critical as long as it's between 18 degrees and, say, 28. On this 10 degrees temperature range, the phase diagram you can find in books is valid. You can work with that. The pH? In that case, you mean if you want to buffer the THF water system, yes, it will have an influence, but it's not the pH, it's the ionic strength that will have an influence. If you put salt in water, you get a physical chemistry effect which is called salting out. If you put salt in water, the salt is pushing everything organic which is dissolved in water in the organic phase. So it would move this line even closer to the border, making even less hexane in the system. But this is true if you go 10 grams per liter. When you buffer, you go 10 to the minus 3 molar, which is less than 1 gram per liter. So it's, again, it would change the line in a way you won't notice the effect. So it's not critical. You can work with buffering the THF water system with no problem. It will work.
Thinking about the reagent system, I could predict what happened. Thinking about the variation that the systems goes through.
Yeah, so this is not part of this course, but why is it useful, this kind of diagram? If you have a very long tie line, which seems to be the case in this diagram, if you have a very long tie line, it means the composition of one phase is completely different from the composition of the other phase. So you will have partitioning that are likely, I just go in that phase and not at all in the other one. It will be difficult with a long tie line to have partition coefficient close to 1, small partition coefficient. You will have extremely small partition coefficient, 0.01, and the other compound will have 12 or 20. And you will try, how can I get the partition coefficient closer to 1? The answer is, in this diagram, you have to go with a tie line which is smaller, which means put more THF. If you put more THF, and if the one we estimate is a little bit like this, you go with shorter tie lines, and you are more likely to have less difference between the two phases, and your compound will partition better. So the coefficient, the partition constant will decrease, getting closer to 1, and you have more chance to be able to work with this system. So there is no rule, because sometimes you want a big difference in partition coefficient. I want to extract all the fatty things which are very apolar from my polar molecule. So then you don't need a CCC machine. You can do it extracting. Very often you extract the compound you don't want, and you keep the other one in the other phase, because the partition coefficients are really different. But if you want to partition similar compound, you may have to work with smaller tie lines. So that's, in that case, smaller tie lines means a lot of THF. You have many phase diagrams that are more lower, so you can work with less common solvent, and that would be easier to butanol. We have a case which is butanol, water, maybe ethyl acetate. Butanol acid acidic water is just very low. As soon as you put too much acetic acid, you have 1 phases. So you should be very low in acetic acid, and that makes short tie lines.